Welcome everybody in the lecture hall on Zoom from the future. So today I'm going to continue. I'm not sure if I will finish, but at least continue this part on the lessons learned about relational database management systems and SQL. Before that, I have two questions. Well, no, one question. The other one is at the end. One question for you, which is right here. How familiar are you with relational databases and SQL? So your first reaction might be, what is this? Or you've heard of it, or you have programmed in SQL from personal websites and you know about select from where, or SQL indices optimizations and query plans have no secrets for you. All your data is in the 6 normal form and you program your games in SQL. All right, so it looks about right. That basically corresponds to the fact that many of you had a bachelor's level lecture on relational database management systems already. And so you are in familiar territory. And as I said, for everybody else, just learn SQL. I will rehearse it a little bit with you. You'll have exercises. SQL is so famous that you can type on a search engine like SQL tutorial and you'll find plenty. So it's really, really easy to learn. All right. So where were we? I was talking about the relational algebra, which is what SQL actually implements. And I gave you 3 things that we can do with tables. The first thing was selection, which is about taking some rows, but not all rows. Projection, which is about taking some columns, but not all columns. And grouping or aggregation, which is when you have a large table and you want to compute aggregates, right? It's typically what the statistical office, cantonal or federal, is doing with the data. Well, then we have sorting. Sorting means that you take a specific column or multiple columns and you rearrange the order of the records, the order of the rows or the business objects, sorted, for example, alphabetically, and that gives you the same table basically, but in a different order of the records. Now, you remember that I told you about the different semantics that the relational model can have, depending if you consider lists of records, sets of records, or bags of records. And obviously, if you want to sort the records, that only makes sense if you have a list semantics, because the order actually matters. If you have sets or bags of records, then sorting will do nothing, because the order doesn't matter if you have sets or bags. Okay, but most systems that you have, like PostgreSQL, they support sorting because they are based on the list semantics. Then we have the Cartesian product. Use at your own risks, because this is the best way to crash your computer. Some do it during the exam. You really need to be careful about what you're doing. So the Cartesian product, if you consider, let's take the set semantics. So the first table R is a set of 2 records, 2 rows. The second set S is a set of 3 records, and you take the Cartesian product of that. That's 2 times 3. So you basically take all the possible combinations of a record from R and a record from S, right? So that's 2 times 3, 6 possibilities. Now you can imagine if you have 1 billion records in the first table and 1 million records in the second table, that's going to give you a quadrillion records. And unless you have a data center, then that's going to crash your machine, right? But Cartesian products are actually very rare. It's a primitive operation that we have, but it's rare to actually do a Cartesian product. Rather, what people typically do is they only take a subset of that Cartesian product. They only take the ones that match. For example, take the columns B and E, and you only want to retain the records where B and E are equal. That would be the first one, and that would be the 5th one, right, where they are the same. And so typically, if you join based on B and E, for example, you would only take this one and get this. And because B and E are equal, you only retain one of them. It doesn't matter to have also E here because that would be the same values. That is called a join. A join is a fundamental thing to do with tables. It's very important. We'll see that it's also expensive, much more expensive than projection and selection, but we will see that. Well, now, a specialist of algorithmic complexity would tell me, no, it's not expensive because you can do a join in linear time with hash tables, but there is theory and practice, right? In practice, if you actually want to do a join, it is a bit more efforts than just a selection or a projection. Okay, so we have joins. So that's actually the most important primitives, right? Projection, selection, aggregation, sorting, Cartesian product, join. There's many others, but these are the most important ones. Now, there is a whole domain of the database theory called database design theory, which can be summarized as best practices and avoiding design mistakes. Maybe some of you already encountered these problems when you try to build a website and you have to figure out the schema of the data that you have. Imagine it's a web shop and you have a database with all the products and the customers and the orders. If you don't put the data correctly in the table, you're going to start having problems. And these are problems that have to do with the fact that the data is duplicated or stored several times, or you're trying to put too much in the same table and so on. These are called anomalies, right? So you can have update anomalies, delete anomalies, insert anomalies. The summary of that is basically that if you store your data multiple times and you update it, you might forget to update it everywhere it's duplicated. And then you run into an update anomaly. Right. For this reason, there's a whole theory of mathematical theory that has been designed to try to help people into good practices. And there's a whole bunch of definitions that we have, like functional dependencies, normal forms, and so on. For whom does that ring a bell? Okay, for many of you. If it doesn't, then don't worry, you'll see why you don't have to worry about this. But let me talk about functional dependencies. Imagine I have this table. I say that I have a functional dependency between these two columns if the second one depends on the first one. How do I see that there is a dependency? Well, every time we have this value in here, we always have big data. So it's kind of, this column is a function of that one, right? If you know the value here, you have a mathematical function that gives you what's going on here. That is called a functional dependency. And again, in functional, there's function. Basically, this is a function of this. Functional, do we have a question over here? Yes? Yes, so let me repeat in the microphone what you asked, if I correctly understood you. Basically, you're saying that since this is a function, maybe we could just remove that other column that depends on the first one and instead evaluate the function, right? It's a good idea. Let me tell you more about how we would implement that. There's two ways to define a function in math. There's something I think it's called extensional and intentional, two ways to define a function. An intentional function, if I'm correct, is when you give a formula, x maps to x squared, right? In that case, you can compute something based on the value. The other way of specifying a function is extensional, meaning that you have an exhaustive list of all of the values plus what it's associated with. This is in fact called a table. So if you want to implement what you said, you're correct. You would basically create another table with the correspondence between these two and then take it out of that one. This is exactly what it means to go to a higher normal form. And a normal form is exactly about doing what you say, of taking this out of that table and putting it somewhere else, right? So your intuition is correct. Okay, does it answer your question? Yeah. All right. So this is a functional dependency. Then we have the notion of a super key. What is a super key? It's a set of columns such that there is a functional dependency from them to everything. It basically means that all the rest of the table is just a function of these. Now, we kind of already discussed that yesterday with primary keys, right? A primary key does exactly that. Well, a primary key is basically a super key, but it's a super key that is optimal, that is minimal, because a super key could actually be a superset of a primary key. In fact, you could take the whole set of columns that would be a super key, right? So a super key is just when you try to find a primary key, you start finding the super keys, then you take a minimal super key, and that gives you a primary key, right? So again, a super key is a set of columns that determines everything in the table. And then you try to find the minimal ones because you might realize that this is too much, that there's superfluous columns here, so you can remove and realize that only these two are enough, right? That's a minimal super key. You cannot remove anything anymore. That's called a candidate key. Why candidate? It's a candidate for primary key. You might have several candidate keys, and then you select one of them as the primary key of your table, right? So super key, a minimal super key is a candidate key, and one of the candidate keys you decide as the designer, this is my primary key that you can define in SQL, okay? And why am I saying that? Because there can be multiple candidate keys. This is also a candidate key. And the decision is basically yours. You basically take the most meaningful one, right? So this is probably more meaningful than this one. Then you have a lot of theory. You have the notion of a non-prime attribute, prime attributes, and so on. A non-prime attribute is basically an attribute that is never in any candidate key, right? A prime attribute is something that appears in some candidate key. So leggy and lecture ID and name would be prime attributes. CT is not a prime attribute. It's a non-prime attribute. So based on that, this is just some math definitions, we define the normal forms. And that almost sounds like music, right? When you have all the notes and you know, a second, a third, a fourth, a fifth, and so on. When you have a first normal form, a second normal form, a third normal form, a 3.5 normal form, a fourth normal form, and so on. It goes all the way to 6. Maybe people will invent more. What's the first one? Well, the first one, good news, I already told you. I just didn't call it that way. This is atomic consistency. You remember atomic consistency? When you don't have a table in a table in a table. Well, this is also called the first normal form. That's another name for it. So that's the first level that you might require for good design is to not have nested tables. You forbid that. You only have flat atomic values, strings, dates, numbers, and so on. That's the first normal form. That's a counterexample that we also saw yesterday. That was a counterexample of atomic consistency. All right, and this is an example of the first normal form. Nicely flat, looks like these clay tablets that I showed you, or a nice spreadsheet. The second normal form, well, every time we go by one level, we keep introducing more and more and more requirements from our table. The second normal form, typically it's taught at the bachelor's level too, means that you don't have the right to have a functional dependency with a strict subset of a candidate key. So it means not the entire candidate key, because the entire candidate key would determine everything, but you take less than a candidate key. It cannot functionally determine a non-prime attribute, right? Just take it as a face definition, face value. So that is, for example, here the case that you have leggy. Remember that a candidate key was leggy and lecture ID. If I take leggy, that's a strict subset, and it functionally determines CT. It means CT is a function of the leggy. That is forbidden in the second normal form, right? Because CT is non-prime. It's not in any candidate key. Okay. The third normal form takes it even further and says, not just a strict subset of a candidate key, even more generally than that, anything that's not a super key. That's an even stricter requirement. Anything that's not a super key cannot determine functionally a non-prime attribute. A non-prime attribute cannot be a function of something that's not a super key, right? That's an example. For example, CT state is not a super key. It's not even inside a candidate key. And that functionally determines a non-prime attribute, right? The postlight sal, the zip code, is dependent on the CT and the state. If I give you a CT and a state, you can give me a zip code, right? Of course, it's an oversimplification of reality. I mean, in Zurich, there's multiple zip codes, but just to give you an idea, right? So that's the third normal form. The 3.5 normal form, it was called that way because it was figured out that it was between 3 and 4. It's also called Boyce code. Code is the same Edgar code that I told you about. Even stricter, we still have something that's not a super key, but it cannot functionally determine anything. Prime, not prime, we don't care. Anything, right? The only thing that can functionally determine something else has to be a super key. So that's, for example, a counterexample that is something that's not a super key that functionally determines something else, and that's forbidden. Okay. So that's an example of the Boyce code normal form. When I teach big data or information systems to non-computer science students, the only one I teach them, so there's the first one, of course, the atomic easy, but that's the Boyce code normal form. This one is actually easy to understand. You cannot have something that is not a super key and that functionally determines something else. And now I'm coming back to the remark that you made earlier. In order to get to these normal forms, it's actually quite intuitive to explain. You just need to make sure that you organize your data in tables, and one table does one thing. You have one table for your products, you have one table for your customers, you have one table for your orders, and so on and so on. One table for one thing. You cannot have a big table that stores too many things. That's how you break normal forms. And by having one table for everything, each table does one thing, that's how you get into normal form. That's the intuition. Now that's very complex. We actually, what I told you here, we spent several weeks of that on the bachelor's level to actually go through the normal forms. You can do a lot of math, a lot of formal proofs with actions and so on, a lot of notations. So it can get very scary. Well, I have good news for you, especially to those of you who never heard of normal forms before. Okay, well, I have good news. We're going to drop them. We're throwing them away. I told you we would break rules in the big data lecture. So everything you learned during your bachelor, like all the good design of normal forms, in big data, we throw it away. You will see data that's not in normal form. You will see data that is in a huge big table that contains a lot of things. You'll have a lot of functional dependencies in there that would be normally undesirable. But in big data, we do it. And there's a reason why we do it. It's in fact because we analyze the data. We don't update it or modify it. And this is why we don't care about normal forms so much. Now, don't get me wrong. I'm not saying that learning normal forms was for nothing. That's not what I'm saying. It's still very important if you have a database that gets updated all the time, like a web shop, right? Then you need the normal forms. But when you analyze the data, you can drop them. So that's the reason I told you, don't worry about normal forms, because we're actually throwing them away, right? But in order to throw them away, normal forms, you at least need to understand that they exist, and you need to know that there are reasons why we are throwing them away. And I'll come back to this when we actually do throw them away during the semester. There is a name for this. It's called denormalization, right? We denormalize the data. And by denormalizing the data, we are actually going to make it easier to put it on a cluster and query it in parallel. These are all the intuitions I will give you during the semester. Today is just a general explanation, but we will really take the time during the semester to understand what it means to denormalize the data to get rid of normal forms. In fact, we can even denormalize all the way to no normal form at all. I told you we would break the rule also of atomic integrity. In this lecture, we will see tables in tables in tables in tables. We will see that, right? We will see that these are trees, but that I'll come back later. Okay, so that was the relational algebra, and that was database design theory and the normal forms that we're anyway going to throw away in this course. Okay, so now I'm going to SQL. SQL is this language that you really need to learn it, because you will see that it will come back in big data technologies as well. So that's the landscape of languages, right? You know, in software engineering, originally in computers, you have this assembly code, right? The very low level language. And then some languages emerge like COBOL, Fortran, C, C++, Java, Python now, which is even more modern. So you have this kind of two levels. I would call an assembly code a proto-imperative language. And then you have imperative languages, right? Java, C++, and so on. It's for loops, you know, while loops, all that kind of things. That's in software engineering. Well, it turns out that in databases, we have exactly that same distinction. We have these low-level ways of querying the data, typically with APIs or proto-declarative languages. I'm thinking of Pandas, of the MongoDB querying system, Apache Spark, the API. All of this is a proto-declarative language. Then we have the high-level languages that are often functional. The most important use case for functional programming languages is data queries. If you want to query data, you want a functional language. This is what SQL is, SQL. Right? It is a functional language that allows you to query the data in the high level. It should really see as something like Java compared to assembly code for the API. Like Pandas would be assembly code and SQL would be the high level. The same goes in machine learning. You might have heard about Scikit, TensorFlow, and all of these libraries. This would be the assembly code version. And you have people who are trying to design high-level querying language for machine learning, that you just define your machine learning pipeline on a high level. And this is actually starting to emerge a lot as declarative machine learning. Right? It's actually much more complex than it seems. Right, and in this lecture, we'll look at both of these. We'll look at the assembly code of data querying, APIs, and we'll look at high-level languages. But today, I'll tell you about SQL in particular. SQL dates actually back to mostly the same period as the data independence idea, right? It dates back to the early 1970s. The early design was due to Don Chamberlain and Raymond Boyce back then at IBM. By the way, IBM is one of the oldest companies in IT ever. They really existed very early. I think it was the time where the US Census tried to start automating a little bit the data analysis process. That was way before computers even existed, right? That was very early system, mechanical, that tried to process this. All right, so this is where SQL was invented. SQL actually meant a structured English query language, and it was written in this way here, SEQUEL, structured English query language. It was in San Jose in California, in the Almaden laboratory. It still exists today. The name changed over time, but it actually still exists. You need to drive a little bit out of the Silicon Valley, a little bit into the desert, and then you find the laboratory. The system itself, which was the first implementation of this relational model, was called System R. And the first customer was Pratt & Whitney, which was in 1977. You see, it took a couple of years to actually make it there. But the thing is, do I have it? No, I don't have it here. The thing is, there was a trademark issue with SQL. They got sued by a company who said, no, you cannot call it SQL because that's already a brand that we have. So they had to change it to SQL in order to avoid this trademark issue. But this is the reason why people say SQL and not SQL. We continue to pronounce it as SQL. So you might at some point start saying SQL just like me. I'm saying it because I was in contact with people who say SQL, and then I got used to it. But it's the same. You can say SQL, SQL, just be aware that it's the same thing, right? There are memes about that, by the way, that people contributed last year. All right. Then you might know Oracle, right? That's a company. It was originally called Software Development Laboratories. In 79, Relational Software, and in 82, it was renamed as Oracle. That's one of the early ones. So you already start seeing the big players here. There's IBM, there's Oracle, and Microsoft is the third one, right? The big players in the relational database management system. But basically, the reason why all of these companies were created and worked is that it's actually needed by companies. And today, I think there is not a single company in the world that wouldn't have a database management system, and most often a relational database management system. Also because some of them are free, right? PostgreSQL, you can just get it for free. But it's just absolutely everywhere. You cannot avoid that. So this language is a declarative language. The difference between declarative and imperative is like cooking at home or going to the Mensa. If you cook at home, you have to go through the recipe and prepare the foods, like do this, do that. If you go to the Mensa, you just declare the menu that you'd like to have. I want a veggie menu, I want the street menu, and so on. So This is called a declarative language. It is also set-based. Basically, set-based means that you manipulate billions of rows at the same time, right? In Java, you don't do that. In Java, you just manipulate one object at the same time. This object might be structured, might be a list behind that. But in SQL, you can manipulate billions and billions of rows at the same time. That actually feels great when you're sitting in front of your laptop, Jupyter Notebooks, typing a few lines, and then you have billions or trillions of rows that get analyzed. It's really a great feeling. Okay. That's what I told you about the trademark issue. So SQL or SQL. Who says SQL? Who says SQL? Okay, so you see some of you probably started even before me. If you took it in the bachelor's, maybe that's also how it was pronounced. Okay. So the idea of a declarative language is that you can separate the logical and the physical execution. That rings a bell. That's data independence, right? What it means is that you have a language SQL and you can implement it in many places. You can implement it in C++, you can implement it in Java, in Python, in any language you want, but the user of SQL will not even notice the difference. It's still SQL. So this is really the idea of the physical execution can be swapped, changed for something else without changing the logical model, without changing the algebra, without changing the SQL language. This is extremely powerful because it means SQL is a standard. You can switch to a different management system, a different database product. It's the same language. When I say same, I really mean it like Baseldeutsch or Schweizerdeutsch, Zürichdeutsch, and so on. It's really dialects of SQL. They are not exactly the same, but you basically understand each other. And there is a SQL standard, but you will see you still need to read a bit the documentation because there are small variations between the different SQL dialects. But it's really not much. Okay. So for example, and we will do this during the big data lecture, you can swap the physical execution from a single machine to a data center. Now you have 1,000 machines and you still have SQL running on top, running from your laptop. So this is extremely powerful. Now, it's not only a declarative language, it's also a functional language. A functional language basically feels a bit like math. It's the idea that you have expressions in a functional language that nest into each other and you evaluate expressions. So you basically have a mathematical model that tells you in what set the values that the expression return live. And then you define a formal model that explains the semantic of the expression. And based on this input, you get that output. It almost feels like math when you basically define a functional language. Who knows? I don't know, Haskell or Camel, any of these, right? Exactly. So these are functional languages. And SQL and the query languages we'll see are actually functional languages. I think that pedagogically, when you want to teach functional languages, it's probably best to start with a query language because that's usually more intuitive to start learning than Haskell or Camel. And there are actually people who start doing this in high school and at the bachelor's level. They start with data science and then do computer science for this reason. All right, let's get to SQL now. So SQL basically consists of mainly the select from where. That's the core of it, right? That many people know. Select from where basically allows you to do selections and projections. What this does, select star, means that you keep all columns, the star, from person. So person is just the name of the input table. And where specifies the selection criterion. You select the rows on which the last name is Crusher. Now, if you look at the last name, that's the third column. Only the second record matches, right? This criterion, only this one matches. So you output this table right here, right? So this is the output of this query, given that persons is this table. For whom is that clear? Right? So this is where you need to be careful because it can be confusing. The selection is not done in the select clause, as you might think, it's done in the where clause, right? In fact, in the select clause, you project. Right, so you just need to be a little bit of getting used to. But here you specify a projection of the column. So you select first name and birth date. So you would select this one here and this one here, and you get these two columns. This is what I told you yesterday, right? The selection, the projection. But what's new here is we're doing it with a language. We're doing it with SQL. So this is a selection. This is a projection, right? You start feeling now why it's called a structured English query language, because it was designed to be intuitive, to actually sound like English. Okay. Then we can also do some renaming. So this is as, who, as, when. So that just changes the name of the columns. By the way, just so that I'm clear about what I'm showing here, in purple here, you have the names of the columns. In black, you have the name of the table. And in gray here, you have the types, the domains, right? Because it's domain, we have domain integrity. So all of that is a string. These are just the SQL types, varchar, char, and so on. I'll come back to that, right? This is a date and so on. And the blue, in blue, we have the actual records. Okay, so this is how we rename with as, we can rename. This is how we sort with the order by clause. If we say order by birth date, that's going to now order in ascending order, the birth date. So now we know 4 clauses. Select, from, where, order by. Where is optional, order by is optional, right? But they have to be in this order. Select, from, where, order by. You can also group using group by, right? So you say select from persons group by century. So I'm looking at all the unique values of century. There's only 2, 23 and 24. And then I aggregate the counts. I'm counting how many there are. So there's twice 23 and twice 24. So we have 2 and 2, right? This is an aggregation, and the group by does that. So you have the key here that typically also appears in the outputs, right? That's the grouping key, and that's the non-grouping attributes that is typically aggregated like this, right? So far we have select, from, where, group by, order by, right? They're optional, but it's select, from, where, group by, order by. It has to be in this order, cannot be in any other order. Then we have having. Having, in fact, is like where. It's just that it's after the group by clause. It could have been called where, actually. We see in other languages, it's also called where. But basically, it allows you to also filter out some groups, and you only keep the groups that have strictly more than 2 records. I changed the input, right? So now we have just once 23, and 3 records have 24. So the only group that survives is the group with 24, because only 24 has strictly more than 2 records. Right? So this is why we only keep 24 in there, right? So having is like where, but it's after the group by. So now we have select, from, where, group by, having, order by. You can have a query that has them all, right? Oh, here you go. Select, from, where, group by, having, order by, and I'm throwing 2 more in the process. It's limit and offset. Limit and offset. Think of Google or a search engine. What happens when you type a query under Google? You return the first 10 results. Then you click next. Then you have results 11 to 20, right? It's called pagination. Pagination is done with limit and offset. So if you say limit 10, that's going to be giving you the first 10. Then you say limit 10, offset 10, that's the second page. You jump over the first 10 and return 10. Limit 10 of offset 20 would be the third page, right? And so on. So that's called pagination. You should only use it with order by. If you don't use order by, it doesn't make any sense to paginate, right? Because that's a bit unpredictable. So you really need to have order by. You have to learn this by heart, really. Select, from, where, group by, having, order by, limit, offset, right? Want to try it? Let's do it together. Select, from, everybody. From, where, group by, having, order by, limit, offset. Exactly. That's it. It has to be in this order. We'll see that the more modern query languages relax a little bit the order. You can have it in a different order, but this is really the SQL order. And it's very useful to know it by heart, because then you basically already know a lot of the language. You can skip them. You don't need them all. They're optional, but they have to be in this order. Okay. Now, what else can we do? We can take multiple tables and merge them. When I say merge, there's different ways of doing that. One way is a union. So you take a first table that contains a few spaceships, Then you take a second table that contains other spaceships, and you take the union of that. Now, the union is not a clause. It's not like this select from where, group by, and so on. Rather, you need to take a select from where query like this. Then you take another one and you put union in the middle. Here you could have the whole thing, select from where, group by, having blah, blah, blah. Union, select from where, and so on, right? So you just put union in the middle. So it's not a clause, it's more like a binary operator, okay? Now you notice that 3 plus 3 is 5 here. Why? Because it eliminates a duplicate on the way. You might notice that there is one that appears twice. That's the C. Enterprise C is here and here with the same records. So it just eliminates the duplicates on the way. Okay. Then, okay, you also have, by the way, the intersection. It's called intersect. You also have subtraction, meaning that you only keep those of the first table that are not in the second table. I think it's called except. Is it except or subtract? I think it's except, right? We can look it. I think it's except. So there's union, intersect, and except. These are the three. All right. Then we have the joins. I told you what the joins are about, right? It's basically like a Cartesian product, but you only keep the matching records. So how do we do it in SQL? Well, we use the word join. So you say persons join spaceships. So you express your intention to join these two tables. How do we select the records that match? Well, we basically want to match the last name of a person. That would be right here. That's the last name of the captain. We want to match it with the captain of the ship, where we also have the last name here. For example, Kirk would go here, Crusher, she's not a captain, Janeway goes here, and so on. So you basically combine, but only with the matches. And these are the three matches. Kirk has these two ships, and Captain Janeway has this one. So we have three matches. For whom is that clear? All right, that is a join. It's called theta join. Why is it called theta? Theta just because we specify manually the matching criterion, because it's not the same name here for the two columns. There's also the concept of natural join. That's when the two columns have the same name. Then you just say join and that's it. And it just uses the same name, the columns with the same name to match them. Okay. But if you specify the criterion, then that's called the theta join. Now, what about those that don't have any matches? Well, you have the option to keep them. If you say full outer join, then you're saying, okay, we keep Crusher and we keep the Enterprise D because there's no Picard on the left, right? But what it does, it's going to fill the rest of the table with nulls. Null is a special value that basically means there's nothing, right? It's null. So you just fill the spaceship portion after Crusher with nulls, and you fill the person portion of the table with nulls for Enterprise D. That's called the full outer join. Then you have the left outer join that only does that on one side, the right outer join that only does that on the other side, and the full outer join does it on both sides. So you see, it's very, very powerful. Then you can add natural. That I already told you. Natural is just when it's the same column name. So here, if you want to join, and imagine that I change the name of the attribute on the starships, I also call it last name, then it's the same attribute name. In that case, I don't even need to bother specifying the criterion. I just put natural. It's going to match the column names. But be careful, because sometimes you might have the same column name, but accidentally. So you really need to be sure that this is really the only column names that match, which is your intention. Okay. So this is how you join, and you join always in the from clause. In the from clause, you can have several tables with join in the middle. Okay. And then the magic of functional languages, and that's just like Haskell or Camel and other functional languages, you can nest them. It's just like the dream in a dream in a dream, the table in a table in a table, where you can have a query in a query in a query, right? Yes, we have a question over here. Yes, absolutely. So let me say a few words about this. So null, technically, when you define the notion of the definition of a table as a set of tuples, and then you define the rules, null is not part of the math, right? Null is really something that came up in the practical implementation because it's actually useful. If you want to now think of how does null fit in these rules that I gave you, there are two ways to look at it. The first way to look at it is basically to say that null is like the absence of value. So basically, imagine that you have a table that has missing values. Technically, it would break the rule of relational integrity, but you can kind of fix it by just putting nulls everywhere it's empty, and then you kind of address this issue. So if you consider that null corresponds to no value, then you're still breaking the rule, still not relational integrity. But the second thing you can do is add null to your domain. For example, if you have a domain that is integers, you can say your domain is now integer or null. And then in the tuple, you explicitly add the null as a value, and then you don't break relational integrity. There are the two ways of doing that, two schools of thought, right? Either you consider that null corresponds to no value at all, or you consider that null corresponds to a value that is in the domain, right? And absolutely, you're absolutely right to observe that when you have these nulls filled all over your table, then this starts breaking rules in terms of the relational integrity, right? And again, I repeat, if you consider that null is the absence of value, then this breaks relational integrity. But if you consider that null is a special value, then that doesn't break it, right? Depending how you look at it. For whom does that make sense? Right? Okay. It's really a practical thing. People found out that it was quite convenient to have nulls as a value like this. I'll come back to it, by the way, in a few weeks about nulls, and in particular in JSON and what the absence of value, the actual presence of a null. We will look at all of that in a few weeks, very precisely. All right, very good question. Yes? Then it uses them all for the matches. They all have to match, which is exactly why you need to be careful, because sometimes you might not have seen that there's another column with the same name, and then it might lead to unpredictable behavior. So the natural join, you really need to look at the schema and double check that the columns that are the same are the intended ones, right? Otherwise, you just use a theta join. Yeah, okay. Yes? We should try it. You can try it if you want. I think it would work because technically after on, there should be anything you want. I actually am not 100% sure. Either they allow any expression and evaluate it, or they restrict it. The condition you have here is actually a very specific one. It's called an equijoin. Basically means that the condition is based on the equality between two sides. But you can also have joins with more general criteria, like greater than, smaller than. Could you try it out and tell us next week? So try to put on true, and you see if you get the whole Cartesian product, right? Maybe even more than the Cartesian product. If it's full outer join, you might also need extra cells with nulls on both sides. It's a good exercise, right? By the way, I don't know everything. I mean, it's such a complex product. All right. I will just ask you one last question, and then you're good to go. No more questions? Yes, one more question? That I would need to look up. I don't have an equal keyword in mind. We will look it up offline if we find one. It can also be a different dialect of SQL. Maybe EQ or something. So some languages have EQ instead of the equal sign. Let's take it offline, and I'll take a look at equal keywords. So before you go, please tell me if you followed. And again, today is a bit special. I mean, it's a brush up. Half of you already saw it. For half of you, it's new. But basically, next week, I'll finish this, and then we'll actually start the material of the lecture, right? We'll start studying everything. I will do that regularly at the end of lectures. This is basically so that I accelerate or slow down. If I see that everybody says, okay, that's fine, I understand everything, I can accelerate a bit. If I see that many people say less than half and so on, then I slow down, right? And I can answer more questions. So this is your way to control the speed of the lecture. So now it looks about right. So thank you very much, everybody. I'll see you next week in the other lecture hall at 2 p.m. There is no exercises this week, nothing to worry about. You could try out the Docker if the TA team sends you an email, but that's it. Thank you very much. See you next week.